Hello, everyone. My name is Bruce Anderson. I'm president and founder of 24/7 Solar. Thank you for joining me. I have a very exciting presentation to make about how to get to zero carbon. I'm going to share my screen. All right. A pathway to zero carbon, all electric mining. Goodbye, Gensets. I'm sure this sounds familiar. You're trying to figure out how to get to zero carbon, trying to do your ESG thing. PV and wind only get you so far. Batteries are expensive. And then, how are you going to get those trucks and other equipment to go zero carbon, get rid of fuel? Well, that's a great question. I'm here to show you how to do it and do it profitably. So imagine a pathway to zero carbon, all electric mining. Not today, but sometime in the future on your timeline. We propose a rationally planned, low risk, profitable, long-term plan to become zero carbon, all electric. And you have, as all electric, you can make your equipment all electric, or we will show you how you can make your own hydrogen to power those vehicles. So it's flexibly designed and a pathway, and obviously it gives you bragging rights to say you're on that transition, on that pathway to zero carbon. So I'm going to show you a microgrid that gets you to that zero carbon stage. So you don't have to imagine these things. These things actually exist. This is an all-electric mining microgrid. You get cost savings from the first day. We integrate zero carbon 24/7 solar equipment into your powered equipment, existing power equipment, seamlessly into a 24/7 solar microgrid. And then as you phase out your gensets, as you phase them out, phase in new 24/7 solar equipment that's zero carbon, and ultimately over a period of time, even including your trucks and other equipment, you can get to a zero carbon final destination. Now, at the bottom there, you can see there's that alert about biofuels. Biofuels don't make you zero carbon. Biofuels are made with dirty power. They may be called renewable, but they are not zero carbon. And that's where the world has to get. So in this microgrid, you have the PV, you have wind, you got your gensets as they phase out, and I'm going to show you HeatStorE and a 24/7 solar plant that will enable you to get to that zero carbon level over a period of time. So these are the two solutions I just mentioned. What we call our 24/7 solar HeatStorE battery and our 24/7 solar plant. So I'm going to show you these two things, and then we can talk about how to get there. So the first thing is this battery. Very interesting. This is the very first battery that can operate at full power, even when fully discharged. Now we call it usually our overnight, all-night battery. But nobody really knows how long a storage period they need. This is designed for all night, roughly 10 hours plus or minus. But it also acts as a backup to all your other power equipment because it includes a turbine. And this turbine can burn almost anything, maybe initially diesel because that's what you have, or something else. But if you really want to get to zero carbon ultimately down the road, when hydrogen makes sense, this turbine can burn hydrogen. So this is how it works. At its core is our revolutionary battery. We call it Heat2Power. This is a first. This is a big thing. It's the first turbine that can convert ambient, atmospheric pressure, hot air, directly to electricity with no combustion or emissions. There's no fuel in normal operation. It integrates easily and readily with your existing power equipment. Very robust industrial product, very low maintenance, very long life, and it can also burn fuel. And here's how it works. So the hot air to drive this turbine can come from a variety of sources. It can come from the next piece of equipment I'm going to show you, the 24/7 solar plant. It can come from thermal storage, a heat storage system of some kind, which is part of our battery. And it can even come from a high temperature industrial process. So this high heat, and we're talking over 850 centigrade, goes through a heat exchanger that's in series with the turbine's already built-in low temperature heat exchanger recuperator. So the compressor here compresses the air as normal, passes it through the low temperature recuperator as normal, and instead of going now directly to the combustor, we remove the combustor, we replaced it with this high temperature heat exchanger. So by the time it comes through this high temperature heat exchanger, it's at full compression and full turbine required by the turbine's expander, the turbine inlet temperature. No fuel is required in this. But we've added an inline duct combustor so that when this battery or this turbine needs to continually operate, even though there's no source of high heat, we can still burn fuel. We put that here in this airstream right here. It's not shown. So here's the battery again. All night, we add that to that Heat2Power turbine. We add expensive thermal storage. What's shown here is a cargo container size storage system. And we use sand. This is shipped to the site empty and then filled with sand on the site. We've also added a set of electric resistance coils. This is the mechanism by which we convert electricity into heat and then blow that heat. We blow air through it and use that hot air to heat the storage. And then we move hot air through it when the turbine needs to power to produce power. And again, that inline duct combustor can burn the fuel that the system may require when the battery is fully discharged. So it's pretty clever, very, very simple, very long-lived, very robust. So the next piece of a path to get to zero carbon is our 24/7 solar plant. It looks like this. These are multiple systems. In the lower left is a single system. A single system today is about 400 kilowatts. The same system tomorrow, as we increase the size of each module, standardized module, will be about 2 megawatts. Now, these don't use any water. This is not a steam system. Okay? It's scalable, it's uninterruptible, and we can finance it for you. Here's how this works. We integrate the HeatStorE battery, which is the thermal storage system, and the turbine, but instead of using electric resistance coils to heat up the storage system or to power the turbine, we use the sun. And the way we do that is to take heliostats, solar mirrors, a field of them, reflect the sunlight up on top of a truss tower. It's only 35 meters, 30 to 35. And we heat air to almost 1,000 degrees. That's what's used to heat the battery, not electric resistance coils. This means that we can operate the turbines during the day when the sun is shining, and roughly half the heat that comes out of the receiver on top of that tower, the collector, roughly half goes to charge the battery to be used, that heat to be used at night to drive the turbine. And then again, when there's no more solar, the battery's fully discharged, we can drive the turbine using fuel. And when we use hydrogen, it's zero carbon. No gensets are required in this system. This is much more cost competitive compared with diesel. It's roughly, in fact, it's less than half the cost of genset ownership. And the reason, of course, is we're reducing fuel costs, the diesel fuel costs, which are expensive, as you all know, by as much as 90%, depending on the location, the design of the system, the optimization of the whole system against the cost of the diesel power and the gensets. And the thing to emphasize here is that there's very little risk. Turbines operate even more reliably than gensets, and we're suggesting simply that as those gensets are at the end of their lives, you phase them out and you bring some 24/7 solar equipment in on a phased basis. So here's what an all-electric, a zero-carbon all-electric mine might look like. It is a microgrid. It's got the PV array and the turbines, perhaps wind turbines. It maybe has a HeatStorE battery. It may have our 24/7 solar plant. And then these are the gensets that still remain and are phased out over time. And the applications go out to your mine, your facilities, your other facilities, and ultimately to your trucks and other equipment. So you can imagine this. This is a pathway that's very, very understandable, very manageable, simple, robust, highly reliable, will bear the risk for you. We can deploy relatively quickly once we have a signed contract, and we bring a bankable report from a certification third party. This is the company, 24/7 Solar. We have origins at MIT, our technology does, and the company does, spin off. It's owned partly by MIT and the state of Massachusetts. The U.S. Department of Energy liked our technology so much they provide us an enormous amount of funding to develop the basic technology. We have a world-class technology development team. These are some of our partners here, Fraunhofer Institute and DLR, German Aerospace Center in Germany. Worley Parsons, the Australian global utility engineering firm. Oak Ridge National Labs, and Saint-Gobain, the French construction products manufacturer. There is an enormous amount of interest in this technology throughout the entire world, and you can see how active we are here, whether we have projects under construction, active negotiations, proposed agents, sales partners, collaboration partners, and so on. Enormous amount of activity, and this is in spite of the fact that we're only now building our very first commercial scale solar plant and battery. It'll be complete in Q1 for tire kicking, and we're partnering now with early adopter mines for deployment beginning in late 2022 to 2023. So we will provide you with a free feasibility study. We'll work with you to develop a phased zero-carbon all-electric plan for your mine. So let's talk. A free feasibility study, a phased plan to zero-carbon operation, a complete turnkey system, and you can own, lease, or sign a PPA. Here's my contact information. Please contact us, at least for an initial discussion, and see how you like continuing. So that's the end of my presentation. I guess now is the time for us to begin chatting. Thank you very much.
Thank you so much, Bruce. It's lovely to have you joining us live now to take a few questions.
Thanks, Adrian. It's nice to be here. Really appreciate this.
Bruce, we have a question from the audience, from Chelsea Hamilton. She says, thank you, Bruce. Can you talk about the different site conditions that this system would work on? For example, high altitude, cold climate, etc.
Yeah. So the battery, what we call the all-night battery, that can actually operate any hour of the year, and the CSP plant do have similar conditions, similar but also different conditions. The CSP system, of course, needs lots of clear skies, lots of sunshine. The battery does not. The battery gets its source of heat from, could be the CSP plant, could be excess electricity from wind or PV, which is what we're doing in many cases. As far as altitude goes, turbines and engines alike do not like high altitudes. And so we do have to derate at high altitudes, but it can still operate. High altitudes don't prevent its operation. Wind is not affected. I mentioned sunshine, humidity. May have to change out the some of the metal in the system to accommodate that. But generally speaking, where mines are, we can operate.
Excellent. Thank you, Bruce. And perhaps you could just expand a bit in terms of the main differences between HeatStorE and traditional battery electric storage technologies in terms of the benefits for a mining microgrid.
HeatStorE battery, it's a thermal battery that we store heat instead of thermoelectrically, thermomechanically or chemically, is considered long duration, whereas lithium-ion type batteries are considered short duration. Not only because they're so expensive, but because they're really impractical. They don't have a short life. HeatStorE, first of all, can operate between 8 and 12 hours on a full charge, but more importantly, it can replace gensets. It has a turbine, and that turbine can operate any hour of the year, even when the battery is fully discharged. And so this has incredible implications when you think about it. This battery could either be a backup, in a sense, a spinning reserve, could even serve on a base load basis, and it can substitute for any power generation source that happens to go down for any reason it may go down, whether planned or unplanned.
Excellent. And there's another question here from the audience, from Atta or Remen. What is the science behind using the light, what is the science behind using the light to use on solar? I don't know if I'm reading that correctly.
Yeah, what is
the science behind? Okay.
Science. What's the science behind using the sun?
Yes. Sorry. Yeah.
Well, the science basically is that mirrors reflect light. They reflect it up on top of that tower. The light hits something, and when light hits something, it turns into it heats up the surface, and that's how we operate. We have a silicon carbide matrix in that solar collector, solar receiver on top of the tower, and it's a matrix. It has a lot of surface area, but it also has a lot of space in it. So in a sense, it acts like a heat exchanger. The light hits it, heats it up, very hot, over 1,000 centigrade, and then we blow air through it, and that heats the air. So it's basically a heat exchanger. And then that hot air is transferred to the turbine using a blower. When it reaches the turbine, it goes through that high temperature heat exchanger, which heats the compressed air from the turbine to the level that's required by the turbine to fully operate.
Excellent. I'm afraid that's all we have time for. Thank you so much for joining us, Bruce, and thanks for this excellent presentation.
Thanks for this opportunity, Adrian. Great conference.